pH, when the pH probe didn't touch the bottom yet, you advised us not to add water, so what should we do?
The pH probe doesn't touch the bottom? You mean the water?
It doesn't touch the acid.
The water isn't submerged? Okay, then you have to add water.
That's going to change the pH, you said.
You're right. It's going to change the pH. We don't want the pH going too high. The lower we are, the better to see the first equivalence point of a diprotic acid. And so, that means it's more pronounced. Now, what we want is we don't want to add too much water, because the more water we add, the higher up we go. And if you add way too much water, you're going to miss it entirely. And so what we have to do is we have to reach some kind of compromise. You got to cover the probe, but hopefully you'll be able to see this. So we'll just add some water.
Add like minimum amount of water.
Right.
Just to cover the probe.
Right. Right.
And
that means you want to use a smaller, not too small, but a smaller size beaker. That's all. All right, and other question, Kelly?
I have this question too. How do you use the lab quest to keep your data?
We aren't going to be collecting data. We're just going to be reading the pH off the screen and writing it in your notebook.
Writing it in your notebook?
Yeah. The reason is you have to adjust it. You can't just program, okay, at this many milliliters, then I'm going to go drop by drop, right? Because if you see the pH starting to increase, and let's say you start seeing the pH increase and you're still a milliliter or 2 milliliters away from where you're projected to go drop by drop, then you have to adjust right away and start collecting at drop by drop intervals. So this is where you take on all the inputs that the information that you're getting, and then you have to adjust the procedure. So if we program that into LabQuest, then that means we could be stuck, because if the LabQuest, what you program in there doesn't quite match, what you're seeing, then you have to start over again. So it makes no sense to make a program for this, because we have to adjust it as we're doing it. And this is why the lab procedure, there is a written lab procedure for this, but so many people screw it up because they don't make any adjustments to the written lab procedure. They just follow it verbatim, which sometimes can lead to trouble. That includes the dilution. So this is, all you're trying to do is get the best possible data you can, and you keep an eye on the pH as we're going along.
We're going to measure the pH using the lab question, right?
Measure the pH using the LabQuest, not in the LabQuest. We're just using the LabQuest as a pH meter. That's it. LabQuest is capable of recording data. You can program it to record data at certain intervals. You can do that, but we aren't doing it. You probably did that in Chem 1A. When you were doing the temperature in the calorimetry, the temperature measurements in the calorimetry were set at 1 minute intervals. No problem. 1 minute intervals, that works, right? Mm-hmm. But in this case, boy, if where the action occurs is between those, let's say you collect data here at 1 minute, and you collect data at another minute, but the action happened halfway between those, you missed it completely. And so this is why we can't do that. We can't program it like this, because we don't know how accurate our trial titration was. If our trial titration was off slightly, then we have to make adjustments to how we collect our data. It makes no sense. And so what you do is you keep an eye on the pH, pHs, and when you start to see it climb, then you better slow down, because it's going to happen very fast. Well, there are people, they saw it climb. Oh, it just went from 2 to 3, and then 3 to 4, and they're thinking, oh, it's just going to go slow. It's just nice, even. No, it's like skyrocket, and they missed it. missed the whole thing, and they had to start over again. Because their trial, they predicted it was going to occur like 3 milliliters later, but they weren't paying attention. They weren't paying attention to how the data changes.
Wait, so what is our trial titration? What happens if we're not confident in our trial titration?
Then redo it. Trial titration doesn't take any time at all. You just redo it. You've done these kind of Erlenmeyer flask titration, a bunch of them, right? By now, it should be very fast, very easy to do. So if you don't think your trial titration, you hit it spot on, then you redo it. Also, if your trial titration, there's some people, their trial titration takes 3 milliliters. You know, a 1 drop error in 3 milliliters, 60 drops. So 1 drop out of 60 is a huge error compared to a 1 drop error out of 45 milliliters. You know, 1 drop error in 45 milliliters is small error. And so there are people who do, like, their trial titration only takes 3 milliliters because their sample size was so huge. I mean, not so huge, so small, right? Their sample size was so small. And so, you know, for me, I would just redo it. I'd redo it to use a bigger volume, because bigger volume means smaller relative error. You know? There are people who are just totally out, have no clue what's going on in the experiment, and they do the pH titration. The pH titration is 5 milliliters. They're done. They're done in like 10 minutes, and they want to leave. But their data is just, it's garbage, you know? And so they end up redoing it eventually. And so we need to see all the little what we call structural features of the titration to make sure we don't miss any. And it's easy to miss because we are taking big jumps in data. Otherwise, we're going to run out of time if we take it drop by drop for the whole. You know, if we take it drop by drop would be the highest resolution we can get. But it's way too time consuming.
Oh yeah, you said the hump is gonna occur with 1/5 of a drop. You said you cannot do that.
No, I said the pH jump from 4.3 to 7.0 is in 1/5 of a drop for strong acid with strong base titration. That whole thing, the whole rise, takes about anywhere from 1 to 3 drops, and it's done. You're only going to get 1, 2, maybe 3 data points in that, in the big, what we call the equivalence point. And so if you only get, that means we got to be there when it happens, because if you take 1 data point here and then a milliliter later you take another data point here, where is your equivalence point? Well, your equivalence point can be anywhere between these 2 dots here, because let's say it flattens out here. This always happens every semester, by the way. Somebody misses it, you know, is there. And so all of a sudden they didn't know, and then they started collecting drop by drop over here. It's funny, the titration curves. They got lots of data, it's totally flat here. But they missed this, so we don't know. Did it skyrocket right after this? Or right before this? Or somewhere between? And so the error, or the uncertainty in your equivalence point is huge. You can't identify your acid. Because if you use this point, it's you know, you get some molar mass that matches this acid. If you use this point, you get a molar mass that matches some other acid. You can't identify your acid. And so
How come though?
well, we'll talk more about it when we talk about data analysis. The thing we do, what we want to concentrate on for tomorrow's lab is to collect data. We want to collect data. This data collection is very important, and the thing is, you have to have some kind of strategy, mental strategy in your mind about how to collect the data, because we want to get a good data set that we can use to analyze our unknown acid. And so the whole purpose of this is to get a good set of data. And so how can you get a good set of data? Let me get something here. Just show these curves again.
Oh yeah, 2 more questions. endpoint, if it's really pink, then is it okay or is it bad?
It's bad.
Really pink usually is.
No, the thing is, the endpoint is not the shade of the color. The endpoint is it's colorless and then pink. That's the endpoint because you can't tell the different shades of pink. Once it turns pink, which is here, you can see the phenolphthalein is going to go from colorless to pink right at pH 9. Once it's pink, it stays pink all the way out here. And so if you have a dark shade of pink, you have no idea where you are in terms of pH because you can't tell. It just, if you have a dark shade of pink, all that means is the pH is higher than 9. So it could be all the way to 14. And so you never tell by the shade, you tell by colorless to pink. That's the proper way. The pink doesn't have to last very long. It's gonna be a faint pink because only one drop, you know, or less than a drop. Although we're going to do one drop. But you know, for our trial titration, that's what we want to do. We just want to get it within one drop. You know, and it don't worry about the shade because if it was colorless right before that drop, then you're perfect. You know? You could, for a trial titration, you could get a fraction of a drop. It's not difficult to do. For your pH titration, you are not going to get a fraction of a drop. Right? And so this is a weak acid. You can see the weak acid, the equivalence point is very close to the end point here with the phenolphthalein. And so most of them are going to be around here, you know, in the greater than 7 range here. So the phenolphthalein works as a good indicator for a monoprotic acid. It also works good as a good indicator for diprotic acid. You can see here, you know, this is obviously this is a very interesting curve because the first equivalence point is very well defined. But take a look at the starting pH. The starting pH is like 1.5 or so. This is very acidic, and so most likely your initial pH is going to be much higher. Your initial pH is probably going to be about 2 or something, and so it's not going to be as pronounced because the pH is never going to go down when you're adding sodium hydroxide. The pH has always got to go up when you're adding sodium hydroxide. And so, you know, even though if you started at a pH 4, you'd probably catch it. If you start at pH 5, you're just going to see a tiny little blip there. You know, not that you're going to start at pH 5. But if you want to catch the first equivalence point in a diprotic acid, we need an indicator that changes color, you know, in this range here. And methyl orange does. Methyl orange goes from orange to yellow. And so you're looking for light orange here. Here where you would have to look for the shade of orange. That would tell you, you know, it'd be the lightest orange before it goes yellow. Over here, phenolphthalein is a little easier because we go from colorless to color to indicate that. And so if you have a diprotic, you know, we're shooting for around 30 milliliters here. You know, not 20, but 30. And then our burettes hold 50, so we can go to another 20 past our equivalence point. You know, because a lot of people end up stopping right at the equivalence point because they see the phenolphthalein changes color, so they stop titration there. But unfortunately, we can't analyze that curve very well. We need the entire curve all the way to where it totally flattens out up here.
But when do you stop precisely?
You stop when you run out of sodium hydroxide.
Do you start at 50 milliliters?
Yeah, or whatever you start off with. You know, might not start at 0, but you're going to use up your burette basically. You stop at the 0 mark on the burette or the 50 mark on the burette. It'd be the 50 mark on the burette. You don't want to go below the 50 because there's no graduations there. But what you're going to see is it's going to be flat. And so, you know, you take 1 milliliter intervals, nothing much is changing. So just bump it up to like 5 milliliter intervals and then you're done. You know, you could use up the whole thing quickly. But, you know, you want to kind of monitor it and then go bigger. What's that?
This is a triprotic or whatever polyprotic acid.
This
How come
is
it doesn't have 3 curvatures.
Because of the same reason. If we started off with a pH that's too high, right,
So
we're
it's
going to
way
miss the
down.
first one. Well, the problem is our base isn't basic enough. In order to catch the third equivalence point, we need a higher pH base. And so our base is not enough to bring it up to catch that third equivalence.
It's not basic enough to get
It's
it
not
fully
basic
yeah.
enough to see it.
That makes
Right.
sense.
But because the third equivalence point, the actual equivalence point is going to be in the 12 to 14 range. We can actually calculate it. It's closer to 14 because phosphate, you know what's borderline strong base? Tell me what's a borderline strong base. You know the strong base is amide, et cetera, et cetera. Tell me what's borderline strong base, right at the border. Phosphate. Do you see that? Phosphate's right at the border between weak bases and strong bases. So phosphate actually has a very high pH. What we're doing, when we hit the third equivalence point, we've neutralized all the hydrogens, leaving us with sodium phosphate. In order for sodium phosphate to be stable in water, the pH has to be very high.
Makes sense.
We'll talk about this. We'll talk about this because you know, when you have sodium phosphate, like salt, and you mix it with water, you know what happens? It hydrolyzes water, right? It's a base. And so what we end up with is some monohydrogen phosphate, dihydrogen phosphate, and a tiny bit of phosphoric acid. And so what we see is we see speciation. That's why a lot of people, when they think, oh, phosphate and sodium phosphate, well, in a lot of ways they behave similarly because they both have a lot of the same species. And so things like monohydrogen phosphate, dihydrogen phosphate behave very similar to phosphate, and they'll do precipitations or whatever else. Because, I mean, if you have phosphate, you're going to have a mix of species anyway. And so a lot of people, when they think, well, phosphate, oh, that's totally different than dihydrogen phosphate. Well, not really. In metathesis, they're the same. Well, anyway, so we missed that third equivalence point. The third equivalence point is not observed, and the first equivalence point might not be observed either because, you know, this is actual experimental. These are experimental constraints, not theoretical. In theory, we should see 3 humps there, right? But, you know, reality often differs. Like, how accurate were your calculations in predicting the pHs of the salt solutions, or what? I mean, were they right on?
Not exactly.
Not, or close? At least tell me they were close.
Yeah.
Okay, then what's the error? What was the percent error, and why did we have that percent error? You know, these are the types of questions you might not think about, but these are the first questions that somebody's going to ask you. Somebody's going to ask you, if you're doing experimental work, why are your numbers off? And then you have to explain to them why. Okay, so what is wrong then? If your number didn't match the calculation, is it because your calculation is wrong, or is it because your measurement's wrong? And if your measurement's wrong, why is it wrong? Because didn't you calibrate the pH meter? You know, these questions, because we like to talk in terms of theory, right? In terms of, you know, this is how it's supposed to be, this is our calculation. But the reality is, you know, is what people care about. And the reality is, if those don't match, then what's wrong? All this stuff you've been taught about the calculations? And then the next question is, okay, if your pH measurements didn't match your neighbor's, why? And then who's right? Is your neighbor's right, or are you right? You know, when you start doing science, these are the types of things that are going to take up time, your time thinking about, you know, and these are the types of things, if you go to a conference, you're going to be asked about, right? Why was the pH of water not 7, boiled water? Was the pH of boiled water 7? Why not? You boiled it, you got rid of the CO2, why wasn't it 7? Somebody explained that to me.
Or CO2 from the air.
That's what I'm guessing.
Water back down, measured it again, or CO2 from the grid.
Was that? Okay. Some people did the indicator. The indicator indicates it's 7 by the color. The indicator indicates it's 7, but your pH meter shows it's something else. Why? All right, and so the thing is, and this is why I decided to do things a little differently, because the reality is, it's not, you know, when you read these lab write-ups and stuff like that, everything's so clear, everything works out so well, perfectly, but the reality is, it doesn't work so cleanly. You spend a lot of time thinking about that. Well, anyway, you know, these are idealized curves here. Sometimes we get some things that look very good, like the ideal. Like if we did strong acid, strong base, this is pretty good. You know. These are just showing different indicators.
Do you put all those indicators in at once?
No.
Are we gonna use many different indicators?
No, we're only going to use one indicator. We're going to talk about indicators in a minute. These are different indicators we can use to indicate the endpoint, but all these on the vertical part will work. They lead to minimal error. The best one would be this, bromothymol blue. Bromothymol blue is green because what we call the acid color is yellow, the base color is blue. And so right between the two would be green, yellow, and blue. And bromothymol blue is one that you can test your boiled water and it comes out green. It's good. But your pH meter doesn't agree, so what's wrong? You're gonna, you know, if you continue in science, you're gonna have a lot of these. You're gonna have a lot of these things that come up that are going to rack your brain. You're gonna have a hard time explaining, for sure. Okay. Well, hopefully we'll do some more accurate stuff as well. But there are reasons for this. Let's take a look at the titration curves. That's strong acid, strong base. So this would be a strong base in the beaker or flask or whatever, titrated with a strong acid. So it's just inverted. Equivalence point still 7. This is atypical because we usually put the base in the burette. Here's a weak acid, and so this is acetic acid. And so we'll look at different regions of this, and we're going to do some calculations. So this is equivalence point. When we're dealing with a weak acid, strong base, we want to know how the initial pH. Initial pH is just the pH of 0.100 molar acetic acid, which is about 2.8, something like that, 3. And then we start neutralizing that. Okay, from here to here, this is called the buffer region here. And from about here to here, we could use the Henderson-Hasselbalch equation. Even though we can use the Henderson-Hasselbalch equation at the extremes, it's not a very good buffer because it's too lopsided. You know, at the extreme over here, this is almost just like acid, pure acid, because you have so little base in there. And over here, this is almost like just all base, no acid, you know? But we can use the Henderson-Hasselbalch over a much larger range. But as far as the buffer is concerned, the buffer is just a pKa plus or minus 1 is where it's going to be the flattest, you know? But why do we call that the buffer region? We'll talk about that. And then we have the equivalence point, and then we have the excess strong base region. And so we're going to do some calculations here for this. And so what we'll do is we're going to put 0.100 molar acetic acid in here. .20. We'll go 25.0. No, let's go with 30 because that's what we're doing for our titration. And our burettes read to the nearest tenth of a milliliter or to the nearest hundredth of a milliliter? Hundredth of a milliliter. So I'm gonna go with 30.00 milliliters of 0.100 molar acetic acid. And then we're gonna titrate this. I'm gonna keep the numbers simple with 0.100 molar sodium hydroxide. All right, and so what we should be able to do is we should be able to map this out because this is a monochromic acid. And so at 0 milliliters, we have just 0.100 molar acetic acid. 0.100 molar acetic acid has a pH around 2.8. We've done that calculation before. I can't remember the exact number now. And then the pH goes up a little bit and flattens out. And then we see the steep rise here. This steep rise is only, how many pH units do we have? So we're going about 6 to 11 or something, 5? About 5 pH units, 6 pH units. And so it's not as big of a jump as the strong acid. The strong acid is a much bigger jump. All right, and so the equivalence point, where should the equivalence point occur at?